Good afternoon, my name is Connor Kearney. This is my NCalc final project. I did it as a presentation. So there's a slideshow and then I have some scratch work of things I did to work out and find my attack functions. So without any further ado, let's get into it. Little introduction there, hope you like it. So for starters, I just wanted to go over who my team is. So my first Pokemon was Mewtwo. He has 120 hit points. He's a psychic type, and his attack function was attack function A, which I called Spinning Swirl. And it was f of x equals 1 over 1.645 x minus 50 squared plus 99,997 y minus 99.7 squared equals 1510, the course number. My second one was Slowbro. He only had 25 hit points. He's a water type. His attack was attack B, and I call it Lame Leap, and it's R of t equals 5t squared minus 5 over 6t to the third power. And finally, my last Pokemon was Gyarados instead of Dose, because it's a it's a coastline function. I thought it was funny. He has 110 hit points. He's a flying type, and here's his function, attack C function. I called it Coast Curves, and it reads f of x equals 1 over 4 cos x plus 79.7. So whenever I was deciding hit points for them, there are many ways to go about deciding it. It just had to be an integer, and the sum of all three Pokemon could not be larger than 255. And lastly, the value of the highest Pokemon's HP could not be greater than the sum of the other two's HP, which is the triangle inequality confirmation. So I first took into account how much damage I was expecting each Pokemon to do. Mewtwo had attack function A, which was the strongest, and he had a good bit above a 99% chance of doing around 99.7 damage points. Gyarados had attack function C, and he was really guaranteed to do anywhere from 79.45 to 79.95 damage points. But Slowbro with attack function B was at best only going to produce 20 damage points. And I have all the scratch work showing my process of figuring these estimates. So going off my project's work, and I was 90% confident I had optimized attack damages, I knew that nobody's Pokemon can do over 100 damage, because attack function A was capped off at that Y coordinate, at that line for the box would be at 100, so it definitely couldn't be more than that. And attack function C was at 80, I believe, so it can't do more than that. So, yeah, and that kind of is what I was saying. And then this made me realize that if two Pokemon had over 100 hit points, they'd be able to at least take 2 hits in battle, no matter what, because the amount of health they had after the attack doesn't matter. So I decided that since Mewtwo and Gyarados were almost guaranteed to do at least 4 times the damage of Slowbro, I would rather have 2 strong and powerful Pokemon and 1 weak one, rather than try to balance HP with respective attack damage. Pretty much I was not going to let Slowbro drag the others down with him if I tried to balance out hit points to weakness and whatnot. It just didn't make sense to me. So finally, going off my assumption, I decided to give Mewtwo 120 hit points, Gyarados 110 hit points, and this left Slowbro with only 25 hit points. And obviously 120 plus 110 plus 25 is 255, so we're good there. And 110 plus 25 is greater than 120, so it conforms to each criteria of that triangle inequality. It is impossible to tell if this is the right decision before the battle actually happens, but I mean, after much thought, using my attacks as examples, the decision of making Mewtwo and Gyarados guaranteed to survive 2 or maybe even 3 attacks justifies the need to supply them with much more HP than Slowbro. I want my Pokemon that deal the most damage to be able to survive longer, because their attacks are worth 4 slow roast attacks, so it's really a no-brainer. And I will be turning all of this in, but I mean, I have, my thought processes on paper of determining, what attacks they do, as well as, like little math, making sure it conforms to the criteria for HP optimization. But all of this will be turned in, along with my presentation, of course. So now, we can start looking at the attacks. So this is attack A's graph on Desmos. As you can see, on the recording, it probably looks like it's flat line. It's not. It's a very, it's shrank to be almost like a straight line, but it's a ellipse is what you'd call it. And the attack equation is f of x equals 1 over 1.645 x minus 50 squared plus 999,997 y minus 99.7 squared equals 1510. So when making attack 1 or attack A, I had to make sure my implicit function f of x and y was equal to 1510, the course number, obviously. And I also had to make sure the function never went outside a box with coordinates at 0, 0, 0, 100, 100, 0, and 100, 100. So I started off with x squared plus y squared equals 1510. Just your basic perfect circle with the radius of the square root of 1510, which is 38.859. And I began to think at how I could convert this into like that ellipse shape that had as small of a vertical radius as possible and as long of a horizontal radius as possible inside that box that I was allowed to be in. So naturally got on Desmos, translated the center of the circle right 50 units and up 99. Now that the circle's center was in the the right area pretty much, I had to make sure it fit the required coordinate points. So this is where multiplying different coefficients with x and y was helpful. I first learned that multiplying the large coefficient with the y term would make the circle turn into an ellipse that was extremely skinny in the vertical direction, which is good. That's what we were wanting. And the coefficient I landed on was huge, 99,997, because it solved the problem with getting the ellipse into the correct coordinates. Yeah, and it could be above y equals 100. After I did this, the Desmos graph was looking pretty good, but there was a problem. We had about that ellipse shape on each side from 0 to 100. There was about an 11 unit gap on each side. So this was a problem because my Pokemon's damage was determined by a random number from 0 to 100 being generated, and the average value of all outputs for that input on 0 to 100 would be my attack damage. So if there were no outputs on a value, so 0 to 11.2, 88 to 100 in my case, my Pokemon would do no damage, which obviously in a battle, not good. So in order to fix this, I knew I would have to manipulate the coefficient multiplied to the x value in order to stretch the horizontal radius by about 11 units to maximize the probability of an input on 100 having outputs where damage could be determined. Smaller coefficients in front of the x value will horizontally stretch it, and after some fine tuning on Desmos, I was left with the attack function 1 over 1.645 x minus 50 squared plus 99,997 y minus 99.7 squared equals 1510. I did a lot of the fine tuning on Desmos, just having that function there and trying different things, looking at it to make sure it was right. But there is a little scratch work to go with this, which, like I said, I will also turn in, so you can look at that. Now we can get to attack B graph. So here it is, it's r of t equals 5t squared minus 5 over 6t to the third power. So for my second attack function, the damage done would be found by doubling the speed. So r prime of t at a randomly chosen real number on the time interval 0 to 4. The initial displacement had to be at the origin, so r of 0 would have to equal 0. And the displacement on the time interval could not leave the negative 20 to 100 area. R of t had to be continuous, and the maximum allowable magnitude, which is the absolute value of the acceleration, or r double prime of t, was 10 meters per second squared. And lastly, r of t had to spend equal time on the domain speeding up and slowing down. So speeding up from 0 to 2 and slowing down from 2 to 4 in my case. Figuring out a function that met all this criteria and maximized the speed on the interval was tricky a little bit, and it took a few hours of trial and error on Desmos, and then on paper making sure that it was in compliance with all the criteria. So after numerous functions that either did not meet a certain criteria or did what I thought was too little damage, I finally came up with r of t equals 5t squared minus 5 over 6t to the third. With r of t being a negative cubic polynomial, it gave me the shape that I was looking for, while also having an initial displacement at 0, 0, and spending that equal time speeding up and slowing down. I multiplied the x to the third term by negative 5 over 6 to flip the function over and cause r double prime of t, the acceleration, to equal no more than 10 or negative 10, to conform to that magnitude statement of being no more than 10. I really discovered this function by trying several different renditions of similar, I really discovered this function by trying several different renditions of similar functions, because messing around on Desmos can be a little bit entertaining. So, when we solve, this is me kind of explaining, how I got it to work for all those criteria. So when we solve for r of 0, we plug in 0 to the r of t function, and we get 0 at the end, which is good. Proves our initial displacement is at 0 on the interval 0 to 4. Now, r of t is increasing, it's always increasing from 0 to 4. So we can say that r of t is in the middle of 0 and r equals r of 4. And that's 80 over 3, which is 26 and some change. This shows that the minimum displacement on the interval 0 to 4 is 0, and the maximum is 26.667, keeping our displacement well within the negative 20 to 100. R of t is a cubic polynomial, and it is known that all polynomials are continuous across all real numbers, from negative infinity to infinity. The maximum magnitude is 10, which can be found in by plugging the values of r of t into r double prime of t, or you can graph. The trickiest part was making sure that r of t spent equal time speeding up and slowing down. So to prove that my function did this, I set up a number line for velocity, and under that had the number line for acceleration, which is r double prime of t. I then found the zeros of both functions and plugged in values in between them, and these the points where they were, to find out where acceleration and velocity were increasing and decreasing. Areas where velocity and acceleration shared a sign, which was plus in my case, r of t was speeding up, and areas where velocity and acceleration did not share a sign, positive, negative in my case, r of t was slowing down. And for me, it was the interval 0 to 2, r of t was speeding up, and 2 to 4 slowing down. And there's all the scratch work of how I figured out pretty much everything is also there. Just, it's all too small for me to try to show the camera, which is propped up on 2 packages of paper, 2 boxes, and a calculator box. So lastly, here is the attack 3 or attack C graph on Desmos. It's just the standard cosine function, but with 1/4 in front of it, and raise it up 79.7 to get us right under that y equals 80 benchmark. So attack 3 or attack C gave me much more freedom to pick anything, but there were some constraints. The function had to be on the interval negative 10 to 10. This is because an input value from negative 10 to 10 would be taken and then plugged into the attack function in order to determine an output value. that would be, the damage, the attack inflicted on the opponent's Pokemons. Its range could never go above 80, and there had to be at least 2 critical points and at least 1 point of inflection. So when I heard that, I automatically thought of the trig functions cosine, because it's my favorite, because it's symmetrical about that y-axis. And in order to make the output value as large as possible, just never above 80, I vertically translated the cosine function up to 79.5 at first. After this, obviously, came to face another problem, which was just standard cosine x plus 79.5. Amplitude would just be at 1, which would bring us above the 80 benchmark whenever cos goes at that the top curve. So had an amplitude that was too high. In order to fix this, I knew that I would have to multiply a coefficient smaller than 1 to cos x in order to shrink that amplitude in order to fit into that x y equals 80 line. So the function became 1/4 cos x plus 79.7, because after I made the amplitude shrink to 1/4 instead of 1, I could also make it 79.7. After in all of this was to maximize attack damage, but also keeping it in the acceptable range. So have all this scratch work. I'm not going to go off it here, because this is really just to show you. In order to make sure my attack function did have at least 2 critical points and a point of inflection, well, first of all, cosine is literally just a continuous loop of critical points, like minimums and maximums, just infinite. The 2 critical points my attack function had are maximums at the x values of -2 pi, 0, and 2 pi, and it had minimums at -3 pi, -pi, and pi, and then pi over 3 pi, sorry. The y values for these maximums are 79.95, because that is the biggest y value of that cosine function that's 1/4 and then translated up. And that's just me explaining it more. 79.7 plus 0.25, because that's the amplitude. Yeah. And for the minimums, you would have the graph's center line minus 0.25, which is 79.45. I found the CPs by setting f prime of x to 0 and testing between beyond each CP to see whether the derivative was positive or negative. After this, I used a number line to classify if they were maxes or mins. And I used a similar process to find the points of inflection, which being cosine, the nature of cosine has it so where there's a lot of points of inflection. He is always switching up and down. I also picked a cos graph because if you look at Gyarados, his body, he's a serpent, so it looks like a function, which I thought was funny. But yeah, they occur where f double prime of x is 0 and f double prime of x changes sign. So f double prime of x equals 0 on the interval -10 to 10 at -5 pi over 2, -3 pi over 2, -pi over 2, pi over 2, 3 pi over 2, and 5 pi over 2. Having each of these values on the number line showed me that at each of these potential points of inflection, f double prime of x did in fact change sign every time. So all of these are points of inflection, and the y value for all these points of inflection are y equals 79.9, because they all happen on the exact center line of the cos function. And it's 79.9 because of our translation. Okay, and yeah. So, like I said, I have just the little bits of scratch work, a couple pages worth of me just showing the work I did to put this into words. I hope my presentation kind of explained things well, and I hope that the cards are pretty cool, because when I was a kid, these were all my favorite Pokemons, especially this guy. I didn't ever do the battles, but I had a few cards until some kid stole them at my school. So this was fun to do, and I hope you enjoyed the presentation. This is what I was filming on also.